Hey there, fellow physics fans. You really went above and beyond this time, bringing us some Feynman. Wow. The Feynman lectures on physics, chapters 13 and 14 no less. Looks like we're in for a deep dive into work, energy, and those ever so puzzling conservative forces.
Gonna be a good one.
Ready to untangle these concepts together.
Absolutely. It's a pleasure to be here. And honestly, those chapters, they're some of my favorites. Feynman, he just had a way of getting to the point,
Yeah.
getting at the heart of why these ideas really matter instead of just, throwing equations at you.
Absolutely, and that's what makes this deep dive so exciting. We're not just aiming to memorize formulas, right? We really want to grasp the why behind them.
So let's kick things off with two words that we use every single day. But in the world of physics, they take on a whole new meaning. Work and energy. What do you think?
It's almost unfair, isn't it?
Yeah.
We use these words so casually,
Yeah.
like in everyday conversation, but physics, it's like, nope, we're giving them a precise definition.
Yeah.
Take work, for example. Just imagine, picture yourself holding a heavy weight out in front of you.
Okay.
Your muscles are probably, screaming at you? You're putting in effort. It definitely feels like work.
Oh,
right?
absolutely, yeah. My arms would be on fire, for sure. I'd be demanding some overtime pay from, well, I guess the laws of physics.
Right. And yet, here's the thing. As far as physics is concerned, you're not actually doing any work on that weight. Not while it's just sitting there.
Oh, really?
Work in physics, it requires that force you're exerting to actually cause a displacement, to actually move the object.
So if I were to, walk across the room with that weight, now that's work being done.
You got it. Now you're doing something. That act of carrying the weight across the room, you're fighting against gravity and all that effort, that translates to work being done in the physics sense. It all boils down to force acting over a distance.
Okay, yeah. That distinction, I'll be honest, it always trips me up a little. But I think I'm starting to see the light here. But where does energy fit into all of this? They seem, I don't know, intertwined somehow.
Oh, they are. They are. Think of it this way. When that force acts on an object, causing it to move, like we were just talking about, what it's really doing is changing the object's kinetic energy, the energy of motion.
Okay, so the work done equals a change in kinetic energy. Is that what we're saying?
You're getting warmer. Now, hold on to that thought, because that's going to lead us straight into the world of conservative forces. These forces, like our friend gravity, they've got a really, really neat trick up their sleeves.
Okay, conservative forces, neat tricks. I'm all ears. What's the secret these forces hold?
It all boils down to paths, or rather the lack of concern for them. Imagine carrying that weight again.
Okay.
But this time, instead of just a straight line, you're taking like a winding path, maybe even like doing a little dance along the way.
I'm picturing it, a physics-themed dance party with a heavy weight. I'm not sure I'd have the energy for that.
Right. But here's the thing. No matter what you do, the amount of work that gravity does on that weight, as you move it from point A to point B, it stays the same, regardless of your fancy footwork. That's the magic of conservative forces, the work they do. Totally path independent.
So gravity's like that super efficient friend who's all about the destination, not the scenic route.
Exactly. And this unique property, this path independence, it's what gives rise to the concept of potential energy.
Okay.
Often symbolized as, you'll see it as U. It's like this energy that's stored, just waiting to be unleashed.
Yeah.
And it all depends on the object's position in a force field. Think of it like, that feeling you get when you're at the very top of a roller coaster right before the plunge.
Oh, I know that feeling well. Pure anticipation, like a mix of terror and excitement all at once.
Right.
So that's potential energy at its peak.
Precisely. You've got all this potential energy built up because of your height above the ground.
Yeah.
And as you plummet down the track, that potential energy, it gets converted into kinetic energy.
Yeah.
The energy of motion. And guess what governs that beautiful transformation?
What's that?
The work done by gravity.
Okay, so connect the dots for me here. How does work fit into this potential to kinetic energy roller coaster ride?
So the work done by a conservative force, like gravity in this case, is equal to the negative change in potential energy.
Okay, let me make sure I've got this straight. So as the roller coaster goes down, gravity is doing positive work, and then your potential energy decreases while your kinetic energy increases.
You got it. It's like this perfect energy handoff. But this isn't just about amusement park thrills, right? These concepts, they underpin so much of how the universe actually operates.
Okay, well, I'm ready to go beyond the roller coaster. Hit me with some more real-world physics.
Let's talk formulas then.
Okay.
Remember how we were saying how work is related to changes in energy?
Yeah.
Well, each of these scenarios, whether we're talking gravity near the Earth or gravity between any two objects, even springs, they each have a specific formula for potential energy.
Bring on the formulas. I'm ready to speak the language of physics.
All right, but no need to be intimidated.
Right.
These formulas are just elegant ways of describing these relationships. Take gravitational potential energy near the Earth's surface. You've probably seen this one before. U equals MEEC.
Right, where m is mass, g is acceleration due to gravity, and h is the height. So a book held way up high has more potential energy than the same book near the floor. Makes sense.
Exactly. Now, let's say you launch a rocket. When it's far, far away from Earth, we need a different formula because the gravitational pull changes with distance. Here it gets a bit more involved. U equals negative GMM over R.
Okay, breaking that down. G, that's the gravitational constant. Those m's and m's, those are the masses of the Earth and our rocket, and r is the distance between them. But hold on, why the negative sign?
Ah, great question. That negative sign, it ensures that the potential energy approaches zero as the distance between the objects becomes infinite.
So as the rocket escapes the Earth's pull, its potential energy due to gravity just diminishes. Kind of like it's breaking free from the chains of gravity's influence, right?
Yeah, that's a very poetic way of putting it. And this concept, my friend, this brings us to something truly awe-inspiring. Escape velocity.
Escape velocity. You mean like the speed a rocket needs to reach to completely break free from Earth's gravitational pull?
Exact.
Isn't that what determines whether something goes into orbit or blasts off into the great unknown?
Precisely. And you can actually derive the formula for escape velocity
Yeah.
using these very concepts we've been discussing, potential and kinetic energy.
Wait, so this isn't just some theoretical number. We can actually calculate how fast something needs to go to escape Earth.
That's the beauty of physics. By setting the sum of the kinetic and potential energy way out at infinity, equal to zero, meaning the object just barely escapes, we get this formula. V equals 2gma, where v is that escape velocity, g is our gravitational constant, m is Earth's mass, and a is the distance from Earth's center. It's how we launched missions to the moon, how we sent probes to the outer solar system.
Wow, so we can use these formulas to calculate journeys across the vastness of space. That's incredible. But I have a feeling this concept of potential energy, it doesn't just apply to planets and rockets, does it?
You're right, it goes even deeper than that, down to the atomic level. Take something as fundamental as, like, the air we breathe.
Okay.
Two oxygen atoms bound together forming a molecule. That bond, it's all about potential energy.
Hold on, from launching rockets to the very air we breathe, that's quite a leap.
But a fascinating one, don't you think?
Yeah.
Imagine plotting the potential energy between those two oxygen atoms. Like, as we change the distance between them, we create what's called a potential energy curve.
A curve. So it's not a straight line. What does that tell us?
This curve, it's key to understanding how atoms interact. It shows us there's an ideal distance between those oxygen atoms, a sweet spot where the potential energy is at its minimum.
So too close and they repel each other. Too far and they're not quite bound. So there's a just right distance for them to, I don't know, happily coexist.
Exactly. And that just right distance is called the equilibrium bond length. It's where the attractive and repulsive forces balance out and the molecule is most stable.
So even at the atomic level, this balancing act of potential energy determines how things come together. It's all connected.
It is. And speaking of connections, there's another layer to this energy puzzle we should unravel. The concept of fields.
Fields. Now those sound intriguing. Are we about to enter, like, the realm of science fiction? Force fields and telekinesis and all that?
Hold your hyperspace jumps for now.
Yeah.
We're talking about fields in the physics sense.
Yeah.
These invisible influences that permeate space, ready to exert a force on any object that enters their domain.
Okay, so instead of thinking of the Earth pulling directly on a falling apple, we can imagine this invisible gravitational field that surrounds the Earth.
You got it. It's a different way of thinking about the same thing, and it becomes incredibly useful, especially when you're dealing with more complex scenarios.
So a field is kind of like the force's area of influence, where it's ready to act if something enters its territory.
Precisely.
Like an invisible force field surrounding the Earth.
Exactly. And here's where it gets even more interesting. Sometimes, instead of working directly with the force itself, it's actually easier and more insightful to deal with this concept of potential, represented by the symbol kite.
Hold on, potential again. Is this the same as potential energy, or are we talking about something slightly different here?
It's understandable to get them mixed up, but they are distinct yet related.
Okay.
Think of potential, this pin, as a kind of map of potential energy across space.
Yeah.
It tells you the potential energy an object would have if it were placed at that particular point in the field.
Okay, so potential energy, the U, that's specific to an object at a particular spot. But potential, that's like a property of the field itself at that point.
You got it. It's subtle, but that's exactly the distinction. And the amazing thing, we can actually derive the force from the potential energy or the field from the potential using a little bit of mathematical magic.
Mathematical magic, huh? Tell me more about this wizardry.
Well, one of the key tools in our mathematical toolbox is the concept of a partial derivative.
Uh-oh.
Now, before you run for cover, it's not as scary as it sounds.
Okay, you've piqued my curiosity. Demystify this partial derivative for me.
Essentially, it's a way of looking at how a function changes when we tweak just one of its variables while we keep all the others constant.
So kind of like seeing how the potential changes as you move just a tiny bit in the x direction, but you don't budge in the y or z directions.
That's the idea. And by taking these partial derivatives of the potential energy, or the potential, we can work our way back to the force, or the field. It's like reverse engineering the physics.
So start with the potential, apply some calculus magic, and bam, you've got the force. That's pretty neat. But can you give me like a real-world example of where this potential and field business comes in handy?
Absolutely. Let's step away from gravity for a moment and venture into the world of electricity. With the classic example, the parallel plate capacitor.
Capacitors, those little components you find in circuits. I'll admit I'm a bit fuzzy on how those work.
They're more common than you might think, and they provide a perfect illustration of potential difference, also known as voltage.
Okay.
Imagine two parallel metal plates, one with a positive charge, the other with a negative charge.
Okay, I'm picturing it. Two plates, opposite charges. What happens next?
An electric field is created between these plates, going from positive to negative. And just like with gravity, we can define a potential difference or voltage between these plates.
So voltage is a measure of the potential difference in an electric field.
Yes.
Okay.
It represents the work needed to move a unit of charge from one plate to the other. The higher the voltage, the stronger the push on those charges.
Ah, I see. So potential difference or voltage drives the flow of electricity. It's all starting to click.
It's all about how these concepts work. Energy, potential, fields, they all intertwine to govern the behavior of, well, pretty much everything around us.
Wow, this is incredible. We've covered so much ground, from planets and rockets to atoms and electricity. It's amazing how these fundamental concepts, they underpin such a wide range of phenomena.
It speaks to the elegance and interconnectedness of the universe, wouldn't you say?
Absolutely. But before we get lost in the cosmos, I remember you mentioning that Feynman, he had a rather thought-provoking view on forces. He believed that, at their core, all forces are actually conservative.
He did. And it's a pretty bold claim that forces us to confront some of our everyday experiences with forces that seem, well, not so conservative.
Exactly, like friction. You slide a book across a table and it eventually comes to a stop. It really feels like energy is being lost there, which shouldn't happen with a conservative force. So where does that energy go?
That's the million-dollar question.
Yeah.
And it highlights the importance of perspective. When we talk about energy conservation with conservative forces, we're talking about the total energy of the entire system.
The entire system. So it's not just about the book, but the table, the air around it, everything involved.
Precisely. In the case of the book and the table, that friction, what's it doing? It's generating heat. And that heat represents an increase in the kinetic energy of the atoms within the book, the table, even the air around it. It's like all those tiny particles are having a microscopic dance party.
So the energy isn't really disappearing, it's just being transformed into a form that's not as readily apparent on a macroscopic level.
That's the key. From a microscopic view, that energy, it's still conserved. It's just a matter of perspective and understanding where that energy is going. It makes you wonder, what other hidden energy transformations are happening all around us that we might not even be aware of?
It really makes you think, you know? What if those everyday forces we always see as energy sapping, they're just hiding their secrets in plain sight?
Yeah, it's all about that entire system, right?
Yeah.
We can't get tunnel vision just focusing on a single object in isolation. We have to consider the bigger picture. How it interacts with its surroundings, how energy is flowing and transforming within that broader context.
So it's like zooming in on what we think is lost energy and then realizing it's actually just bustling with activity at a completely different level.
Exactly.
Huh. It makes you wonder what other hidden energy transformations are happening all around us all the time.
It's a humbling thought. And, Feynman, he had this knack for turning our intuition upside down, challenging us to really look beyond the surface. He wasn't afraid to ask those big, sometimes uncomfortable questions.
And isn't that what makes physics so captivating? There's always another layer to uncover, another mystery to unravel.
Absolutely. It's about those aha moments when things suddenly click. But it's also about, being comfortable sitting with the unknown, with the questions that keep us searching for a deeper understanding.
I have to say, we've covered some serious ground in this deep dive.
We really have.
From those foundational concepts of work and energy all the way to the mind-bending world of potential fields and those mysterious conservative forces. Honestly, I feel like I've been on a physics roller coaster ride through the universe.
It's been quite a journey for sure. And hopefully you, our amazing listener, you're feeling a little more ready to tackle these concepts yourself.
Yeah.
And remember, physics, it's not just about memorizing equations. It's about cultivating a sense of wonder and curiosity about the world around us.
Well said. It's about looking at those everyday things, those little occurrences with brand new eyes, questioning what we think we know, and really embracing the elegance and interconnectedness of it all.
Exactly. Keep those Feynman lectures close at hand, and who knows what other incredible insights you'll discover.
Absolutely. Until next time, keep exploring, keep questioning, and never stop diving deep into the amazing mysteries of the universe.